Hey everybody. Today we're doing infinite sequences. In math, a sequence is just a list of numbers that has a specific order. In calculus and other higher math classes, we assume that those sequences go on forever. That's the only really interesting case. You'll have already seen infinite sequences and just not realized it, perhaps. For example, the even numbers, the square numbers, and the Fibonacci numbers. In each case, these go on forever, and of course they have a specific order. A little bit of notation. We write a sub n in curly braces to denote an entire sequence. And if we start writing things out, then an is going to represent the nth element of the sequence. So a1 is the first, a2 is the second, and so on. There's nothing special about a. We could have done bn or cn. There's two fundamental ways of defining a sequence. You can do it explicitly or recursively. An explicit definition for a sequence just gives you a formula. You plug in the n, and you get back the an. So for example, with the square numbers, an is n squared, and with even numbers, it's an equals 2n. In contrast, a recursive definition for a sequence tells you how to get each new element of the sequence from the ones that came immediately before. The Fibonacci numbers are the most famous example there. A sub n is the sum of the two that came before, an minus 1 and an minus 2. When you have a recursive definition, you also have to give a starting point. You have to say the first or first couple elements of the sequence in order for that definition to be complete. We can represent sequences graphically. We're going to take the n values and put them on the horizontal axis and the corresponding an's and put them on the vertical axis. So, for example, an equals 1 minus 1 over n. When n is 1, I get 0. So I plot the point 1 comma 0. When n is 2, I get 1/2, so I plot the point 2 comma 1/2, and so on down the line. Here's the first 8 or so elements of this sequence represented graphically. Now this picture is suggestive. As n gets larger and larger, it really looks like an is getting closer and closer to 1. That motivates this definition. We're going to say the limit as n goes to infinity of an is equal to L if we can make the sequence as close as we like to that value L by taking n sufficiently large. If the sequence does settle down to that value in that way, we'll say that the sequence converges. If it doesn't, we'll say it diverges. Okay, so in order to be able to tell when sequences converge or diverge, we're going to need this definition. We say a continuous function agrees with a sequence an if f of n equals an. So, for instance, the function f of x equals 1 minus 1 over x agrees with the sequence an equals 1 minus 1 over n. At first glance, it's maybe not totally obvious why we're doing that. The difference between f of x and a sub n here is the domain. F of x has domain all real numbers except for 0. An is defined only on the positive integers. This is helpful because we have lots of techniques for dealing with limits of functions, and we can now bring those all to bear to do limits of sequences. Using this fact, if f of x agrees with an for all n, and the limit as x goes to infinity of f of x exists, then the limit of the function and the limit of the corresponding sequence are exactly the same. So, for example, we said that f of x equals 1 minus 1 over x agrees with an equals 1 minus 1 over n. We know that that function converges to 1 as x goes to infinity, so the sequence has to converge to 1 as well, just using this fact. Here's an example. This one comes up all the time. So r is some number, and we're looking at the limit as n goes to infinity of r to the n. So the outcome here depends on the value of r. If r is less than 1 in absolute value, so we're taking different powers, higher and higher powers of a proper fraction, that sequence is going to converge towards 0 because you're taking a fraction of a fraction of a fraction and so on down the line. If r is equal to 1, then the entire sequence just consists of 1s, so of course it converges to 1. And if r is greater than 1 in absolute value, then r to the n is going to be growing and growing and growing in absolute value, and the sequence is going to diverge. Finally, if r is -1, then when I take higher and higher powers of -1, the sequence is just going to flip-flop back and forth between 1 and -1 forever. So that one is also not going to converge. Here's an example. Does this sequence converge or not? an equals n squared minus 4n plus 3 over 3n squared minus 3n. So we're going to consider convergence for this sequence by looking at the corresponding function, x squared minus 4x plus 3 over 3x squared minus 3x. And let's look at the limit as x goes to infinity. We can do this, for example, using L'Hopital's rule. This is an infinity over infinity form. We get 2x minus 4 over 6x minus 3, another infinity over infinity form. L'Hopital's rule again, differentiate the top and bottom, and we just get 1/3. So we conclude that the limit as n goes to infinity of an is 1/3. All the usual limit laws apply. So let's have c be a constant, and then let's assume that an and bn are both convergent sequences. If we have a constant times an, that sequence also converges, and in fact we can just factor out the constant. If we have a limit of a sum or difference of convergent series, we get the sum or difference of the limits. Same thing with products. Same thing with quotients, assuming the denominator isn't 0. And same thing with powers and roots, assuming that everything is defined. So for example, you don't want to be taking square roots of negative numbers. An important theorem, the squeeze theorem. Suppose we have 3 sequences, and they kind of go in order. an less than or equal to bn less than or equal to cn for all n. And if the bottom one and the top one, an and bn, both converge to the same number L, then the middle one does as well. Here's the picture. We have an on the bottom in red, less than or equal to bn in green, less than or equal to cn. So the picture is supposed to be showing that an and cn are both converging towards something maybe a little bit less than 2. And the point here is that the green sequence bn is also going to be converging to that value as well. Here's an application of that. If the limit as n goes to infinity of the absolute value of bn is 0, then the limit as n goes to infinity of bn is 0. So the idea is just to consider 2 sequences, negative the absolute value of bn and positive the absolute value of bn. Both of those are going to 0, just by hypothesis. We've said that the limit as n goes to infinity of the absolute value of bn is going to be 0. Therefore, we can use the squeeze theorem, since an is less than or equal to bn less than or equal to cn, to conclude that the limit of bn has to be 0 as well. One quick application of that, so the sequence bn equals -1 to the n over n. The absolute value of bn is 1 over n, which obviously goes to 0. So this sequence bn is also going to converge to 0.